Start? Okay, so it's still early morning. Some of you still sleepy. Uh, okay, so just to remind you what we've done yesterday, not long time ago, we started the column discussion. As you can see, the discussion is pure theoretical to give you a background of the column design, which to me is important. For some of you, I know you don't care about the theory. You only care about, how things work in a numerical example. Please be patient. You will see some numbers shortly and more numbers next class. So just to remind you, the columns have classification, so many actually. One of them is where the load is being applied. If the load is applied at the center of the gravity or the centroid of the cross section, then we call this column centric, and the column simply the entire cross section will have uniform stress. Uh, However, if the force or the applied load moves from the centroid of the cross section, causing what we call eccentricity, so the eccentricity, it will cause a bending moment, and this column is called eccentric column. And I think we came to the agreement last class that centric column is pure theoretical, since they are very, very hard to realize in practice, because it's very hard to make sure that the force is applied exactly as at the centroid. However, the eccentric column is more realistic. And what we did in this slide is I was trying to show you what are the sources of the eccentricity. Not all of them. This is only few examples of how the column becomes an eccentric column. So on the first one, in a column, in any moment frame, where the connection between the beam and the column is a rigid connection. So in this case, the columns are eccentric column. Even for interior column of a building, where there could be a unequal load case, for example, live load is on the right span, but not on the left span, and this will cause the deflection or the deflected shape to rotate at this joint, and it will add some bending moment on the column. And then finally, whether in overhead crane or building with overhead crane, or maybe precast building, we always encounter this situation where out from the column we extend the cantilever to support the crane or maybe a beam in a precast building, and this will cause eccentricity as well, as we discussed last class. And now in this slide here, I was talking about the mechanism. If you have a centric column, what will be the mechanism of failure? When you start with zero load, so this means zero stress. As we increase the load, the stress will increase uniformly on the cross section until the strain will become equal to 0.002, which is the yield strain for 400 grade. Now, what happens is the column will still take more load until the strain in the concrete becomes 0.0035, which is the maximum strain in concrete, and this will mark the end of the life of this column. Okay? So finally, what we said is, we said, you know what, mathematically, how we can find the capacity or the axial capacity. Let's be clear. We're talking about axial capacity, not bending capacity, not shear capacity. So which means what is the maximum axial compression force that this column can handle? Not very difficult. It will be addition of two components. A component by the concrete, which is how much force concrete can take, and another component by the vertical bars in your column. Not very difficult. And if we want to turn this into equations, here is the equation. Concrete, you have to multiply the stress, multiply by the area. So we talked about this yesterday, that the stress is alpha 1 multiplied by phi c, and then multiply by F prime C. And this is the stress or reduced stress in concrete, multiply by the area of the concrete, which is the gross area of your column minus the area of the vertical bars. And then for the steel, nothing super, same as we know before. We multiply phi s, and please take a note. You have to change this phi c to phi s, multiply by F field. So this is a reduced stress, and then multiply by the area of the vertical bars. And then finally, your column can take the both of them. You need to add whatever carried by the vertical bars plus whatever carried by the concrete core, and this is will give you your final resistance. The code said you need to multiply this number by 0.9 if your column is spiral column, and by this number here if your column is not spiral, if it's tight column. So that's what we covered yesterday, and today I will just quickly go through a very quick numerical example that trying to find what is the capacity of the centric column. So in this example here, I have this cross section. So my column cross section is a square. It is 500 by 500, and it is reinforced with 8 30M vertical bars and ties, 10M ties at 300 millimeter on center. Also about the material, the concrete is 25 MPa, and the rebar is 400, and some other constant that we know, phi S is 85% and phi C is 0.65. Now, what you have to do is here is you need to find the area of the steel. So the area of the steel is, since our bar is 30M, and not sure if by now you're able to memorize those numbers. I'm confident that probably all of you know that a 10M is 100 mil, a 20M is 300 mil, 25, I'm sorry. 10M is 100, 15M is 200, 20M is 300, and 25M is 500, and 30M is 700. Again, if you're not able to memorize them, there is a table in the code that gives you the cross-section area of different bar designation. For 30M, here we go. The area of a single 30M is 700 mil. And if you want to find the total area of the vertical bars, not very difficult. We have 8 bars, and every bar is 700. So total, we have 5,600 millimeter square of rebar. When it comes to the gross area, which is the gross area of your column, not very difficult. The column is square, which is 500 by 500. So finally, you get 250,000 millimeter. And I would say this is wrong, huh? You know, guys know why it's wrong? Because it's supposed to be here a square. That's in the book. This is a snapshot from the book. It's not my writing. So you can see instructors, they do mistakes. Even the books, they have also some typo error. Okay, so this is supposed to be square because that's an area. So this is 250,000 millimeter square. Now all you have to do is to find your BR maximum is to use the equation. Remember alpha 1 for the non-linearity of your of the concrete in stress and strain in concrete has equation in the code, but as we agreed that in our class, for simplicity, we're going to use alpha 1 for 0.8, and if you remember also beta 1 is 0.9. And so what happens here, there's no super signs. Let's do it. So we multiply alpha 1 is equal to 0.8, phi c is 0.65, f prime c is 25 MPa, and we multiply this by the area of the concrete, which is nothing than the area of the whole column minus the area of the steel. And then, so this part here is how much concrete core can take, plus this is the share of your vertical bars. So phi s multiplied by F field multiplied by the area of the vertical bars. So finally here we get 5,081 kilonewton. this is the BR node. And our column, if you remember, look at this section here. It is 10M ties at 300, and this is how we call the ties. A spiral, there is another call for the spiral. We don't call it by the spacing because it's a continuous like a member that wounds around the vertical bars. So once you see this, or you see even this picture that has a hook here, you know that these are ties. So my column has ties, not spiral. And if you remember, what we do is we go back to our code over there, and need to remind you, BR maximum is 0.2 plus 0.002 H multiplied by R node. How much is my H in this case? Can anybody tell me? I need some help, please. In this example.
500.
Exactly. Thank you so much. So the H, as per this statement here, H is the wall thickness or the minimum column dimension. So 500. And if you put 500 here, so looks like you will get 1.2, I guess. If you multiply 500 times 2 plus 0.2, you will get 1.2. However, look at this. Please be careful. It says less or equal 0.8 BR node. It means this whole math here, this term here, cannot exceed 0.8. So that's why if I go back to here, you will see the 0.8. So I multiplied here 0.8 times 5,081. And so what you get here is 4,065. So if you build your column with those bars with this dimension, it can take a centric force of 4,065 kilo Newton. I don't think this is difficult. It's very easy to understand. How about this part here? This part here is optional. Like, I'm not saying optional. So let me ask you here. So for sure, what is the area of the concrete in this column? Can anybody tell me?
500 squared.
That's the area, that's the gross area. The gross area is 500 times 500. That's correct. But I'm asking you, what is the area of the concrete? Concrete.
So 500 minus the thickness.
500 minus the area of those bars. Like it's 500 times 500 minus the area of 8 bars, if you agree. Okay. Uh, let me give you kind of heads up, and because this will lead us to the next discussion. So if you remember in beams, the area of the steel divided by the area of concrete, what do we call this one? The ratio between the area
Re-
of the steel divided by the area
Reinforcement
of the concrete.
ratio.
Reinforcement ratio.
Reinforcement ratio.
Okay, thank you so much. That's reinforcement ratio. This number was 50%, 20%, 1%. Can somebody just give me a rough number? Was it 80%, 50%, or 1%? What do you think?
1%.
1%. That's correct. I'm very happy that you guys are still remembering this. So I'm asking you here, let me go back to this equation and let me ask you, what is the relationship between the 5,600 and the 250,000? Because that's simply the ratio between this number and this number. It is the reinforcement ratio. And you will be surprised, column is a more heavier element than the beams and the slabs. So slabs, probably they are less than 1%. Beams, probably they are 1%, 1.5%. Columns, they are a little bit heavier. But you know, or you will know in my class that maximum 4%. So we have limit also of 4% maximum. Let me ask you, if this guy here is 100%, and this guy is 1 or 2%, okay? Would you agree that I can simply ignore this term here? I'm talking about, guys, I'm talking about
Yes.
math, huh? I'm talking about
Yes.
math. Can mathematically, do you think I can ignore this guy because this guy is super big and this guy is little to this compared to this guy, like let's say 1%?
Yeah, you can ignore it. It's just a small amount.
It's very small amount. Same as I always give my students an example. Let's say, like somebody who owns, like, very rich, and he has millions of dollars. If he just lost $100, he's still rich. Nothing is gonna change, right? So what I'm saying here, if this is 1%, like 1/100 of this guy to the left, it means so that the difference will be 99% of this guy. Would you agree? If this guy here is 100%, probably I can write it in percentage, probably you can get it better. So if this guy is 100% and this guy is 1%, okay, so the difference would be 99% of your area gross, okay? And that's why here we go, this part here. So this guy, you can see it is the same equation that I mentioned before. The difference is here. Instead of me multiplying my alpha 1 times phi c times f prime c by the difference between area gross minus area steel, then I multiply by area gross. You can see here I multiply by 250,000 millimeters square, and I simply ignored the 1%, and I got a number which will be very close to this number. Look at the numbers. So here I got 4,065 kilonewton, and here I got 4,120, which is very close. To be honest, this is more accurate because really what you're supposed to multiply by area of concrete, which is area gross minus area of steel. However, it gives you a little bit of different force. And again, if it bothers you, you can totally ignore about this part if it bothers you. Okay, so this one, this formula here is more accurate, but it takes more time. But you can just ignore the area of the steel because the area of the steel is only 1% or maybe 2%. So we just multiply by the area gross. Okay. Okay, so now this part here, if you want to enjoy the discussion, good for you. If you want to hang for a couple of minutes until I finish it, it's also good for you. So this discussion here, I'm trying to show you and talk about something called small eccentricity and something called large eccentricity. Okay, so as you remember, and probably studied this in strength of material and and maybe soil mechanics, that once we move the axial force away from the centroid, what happens? Once we move the force from the centroid by distance called E, and what is E? This number, which is a distance, this is called eccentricity. Okay, so this means the stress on the cross section will not be uniform. One side will have more stress and the other side will have less stress. Okay, so I'm talking here about small eccentricity, which means the force is within the middle third of the section. And if the force is within the middle third of the section, what happens is the entire section will have compression. One side will have more compression and the other side will have less compression. Okay, so what you see here is the strain diagram, but you can think of also about it just like the stress diagram. So one side will have more stress and the other side will have less stress. Okay, that's called small eccentricity. And if we keep adding forces here, like keep increasing the load P, what happens is this will simply fail as controlled by the concrete. So at some point, once your epsilon C is epsilon C maximum, and remember how much is epsilon C maximum is equal to 0.0035. So as soon as the force generates a strain equal to 0.0035 on one side, what happens is your column will fail, and this failure is controlled by the concrete, which means it's a brittle failure. Would you agree?
Yes.
Yes.
Okay, so now let's move on to the large eccentricity. So the large eccentricity is simply we are going to move our force away very far from the centroid, which means the E is so large. The E is so large. And what happened here is when the E is so large, what happened is one side will be in compression and the other side will be in tension, and that is unlike the small eccentricity. Small eccentricity, it means the entire section will be in compression, but one side is more compression and the other side will be less compression. If we keep or push our force further from the centroid of the section, then what happens is one side will be in compression and the other side here will be in tension. I'm asking you, does it remind you something that we studied before, just rotated by 90 degrees? Did you see this picture before?
Like in beams?
Like in beams. So turn your head 90 degrees and we have seen exactly the same thing in beams, where this is the strain diagram and these bars here will be in tension and these bars here will be in compression. Those fibers will be in compression. So this is very much like a beam. So a column with large eccentricity, it will behave like a beam. A column with a small eccentricity, it will behave like a column. Hopefully this is clear. Okay. Now, I want to, guys, if you have been again, if you, as I said, if you want to hang for a few minutes until I finish those slides, please come back now. Come back now. Because what you will see or what you will hear right now is very, very important, and there is no way for us to ignore it and pass it. I want everyone to understand the following discussion. Okay, now, let me ask you, which is not very difficult. If I give you this cross section here, and I give you all the dimensions. Let me give you a kind of an example. Let's say you know what? Here is this dimension is, let's say 300, and let's say this dimension here from here to there is let's say 700, and let's say we have here we have here one bar, another bar, okay, and let's say we have here one bar, and let's say here one bar, and just make it simple, huh? Let's say that those guys are we have total of 4-25M, okay? And I will give you also one more information. I will tell you, you know what? F prime C is equal to 30 MBA. Now, without, I'm not asking you to give me the answer right now, but I'm asking you in general, if I give you this problem and I give you time, are you able to give me how much this section can take a moment? For example, let's say my moment is going this way. So my moment is going this way. Can you find for me the MR? So I'm asking you, can we find the MR, how much? Like how much kilo Newton meter that this section can take? I'm not asking you by number. I'm asking you, in my class here, did I teach you at some point, if I give you this shape here, okay? And I know that some of you probably have to rotate. Probably that's my bad. I need probably to rotate. I'm not sure if you can do that here. But if I rotate, can I do that? No, actually, it looks like but let's see if I can group them. Not really. So it's not very easy, but guys, can you please rotate your head? And if I give you a member, which is 300 wide by 700 deep, and I give you the reinforcement and the F prime C, and I go in time back like 2 months ago, would you be able to find the MR? Like how much moment that this beam can handle?
Yes.
I think so. Yes, you can do that. This is nothing more than a beam, huh? Just that I give you the reinforcement, you can do that. I don't want to give you to tell me how much, because I know that this has been like probably 2 months ago, and it's very difficult for you to memorize now. But I'm sure that if I give you the material, you are able to find how much MR. And what is MR? It means what is the moment capacity for your beam. Okay? You guys following?
Yeah, we can. I remember MR.
Okay, so let me ask you, that time when I teach you the beam, was there any axial force? Like when I
No.
teach you the beam. So guys,
No.
let me tell you that what you get is you will get the resistance of this section here, how much it can handle with the moment, but the assumption here is the BR is equal to 0. It means there is no axial force acting on this sections. Okay, do we agree?
Yeah.
Okay, but again, as I said, that this was like 6 weeks from now, and I think your memory is like it doesn't help you. And again, I'm asking you to find for me the number, but I want you to agree. If I give you the time and give you the material back, would you be able to find for me the moment? I think yes, you can.
Yes.
And all
Yes.
I'm asking you is you will find MR, but that time we never applied any axial force to my section. Okay, let me iterate. Can we find, if I give you the same section, but this time we're not applying a moment on the section. So I'm going to get rid of this arrow here. So we're not applying a moment. However, what we're applying is we're applying a centric force here at the centroid. Can you find the PR maximum? By the way, because simply it was here, that was 5 minutes ago. So if I give you the section same as this section here, you will be able to find what is the centric force that applied, maximum centric force that you can apply or will fail this section, okay? So let me write it here. So I'm going to go back to here, and I said, you know what? Yes, of course. So let's do it. So if I give you this section, then you can find PR is equal to, PR equals to this much kilo Newton. But remember, do we have any moment in this case? Do we apply any moment or just
If
pure
it's
axial force?
pure axial force, if it's a
Which means
concentric,
MR in this case is equal to 0 kilonewton meter. Which means in my class, you learn how to analyze and find the resistance for centric column with 0 bending moment. And also in my class a month ago or 6 weeks ago, you learn how to analyze and find the resistance of a beam where it's affected by bending moment with the 0 axial force. Correct?
Yes.
How about this? This discussion is very important because it will tell you what this graph means. Okay, so what happens here? Congratulations, guys! You have made it. You are able to find 2 points on the curve. What curve? The curve that relates the axial and bending moment capacity of any given section. And what are those? Look at this, please. So in this diagram here, this is one of the points. So this point here is this point on the curve. So where if I apply a centric force on one section, a centric force, it means eccentricity equal to 0 and there is no bending moment applied to the section. I'm able to find this number. How about if I apply only a bending moment without any axial force? Look at this. So I'm going to move this one to here. And what you found already is this point on the curve. This point on the curve. Remember, think about it, guys, as XY relationship between moment and axial force. Okay, so on the curve, in my class so far, 100%, you're able to find 2 points on the curve. If I give you this section here with all the reinforcement and all the F prime C, all dimension, you should be able to find what should be the axial force without any bending moment. And when I say without any bending moment, think about as a pair of coordinates, PR and 0. Okay, I'm going to write it down here. So this point as coordinate is going to be PR, comma 0, X and Y. I'm sorry, 0, comma PR. Okay, X and Y, because this relationship between on the vertical, on the Y, it is your axial resistance, and then on the X, it's the moment resistance. So this point here is on the curve, 0 moment, and then axial force is PR. How about this point here? I'm going to write it here. It is going to be pair of coordinates MR, comma 0. It means 0 axial force and MR, moment only. Okay. Now, what happens here what if I apply a combination? What if I apply some axial force, and some bending moment. What will be the maximum if I have combination of them, not only pure axial force or not only pure bending moment? So this curve, okay, I'm going to point out this curve. This curve here is called interaction diagram. This curve here is called interaction diagram, which is the relationship between the bending moment and the axial force that can be supported by a given section. So the section is given, okay, and we're trying to see different combination. We already, as I said, we already in my class so far, we know only 2 points on the curve where there is a pure axial force or there is a pure bending moment. However, the reality is when we apply forces, yes, if it's a beam, then we get a bending moment only, no axial force. And if it's a column, we get axial force only without any bending moment. But I already convinced you here in this slide here that centric column is very, very rare and hard to realize. So what is the reality? The reality is our column will have both. Will have a bending moment plus axial force. Can I get you guys to agree on that?
Yeah.
Okay, so now if we go back to this curve here, which I call it it's called interaction diagram. What does it represent? Every point. I'm going to take a point example. For example, this point on the curve. This point on the curve. This point on the curve, what you can tell, you know what? My column can take this much bending moment. I'm going to give you a number as example. Let's say can take a 500 kilo Newton meter, and on the same time, with this bending moment, it can take axial force of this much axial force, which is, let's say, 1000 kilo Newton. This is the meaning of interaction diagram, okay? It is a relationship between the bending moment and the axial force that can be handled by a given section. Can I hear some noise? Are you guys following?
Yeah,
Yes,
we're
sir.
following.
Okay, so now, so just this curve for you, probably some of you are struggling to know what does it mean, but as I said, every single point on the curve, it represents a different combination of the axial force and the bending moment that this section can handle. And some of you who is following, only the ones are following, they'll say, Tahir, listen, probably there is something wrong with your interaction diagram. How come? How come the diagram will go this way and come back? I know it's kind of hard to understand, and I will do my best to explain it as simple as possible. Okay. So, for example, this side here, it makes sense. What does it mean? It means if I have no bending moment, which is this point here, I get the maximum. You can tell here, I can carry so much. And as soon as I add some bending moment, you can see if I go this way, it means if I go this way, it means I'm adding more bending moment. And makes sense. When I add bending moment, you can tell what happens to the axial force. Am I carrying more axial force or less?
More.
Less.
Less. How come? Look
Less.
at what happens to the axial force. Every point here, look at this dimension. So for example, this point here, it can support this much axial force from here to there, to there. Okay, which obviously it is less, okay, less than this number, because this is the pure centric, huh? Do you get that, Gord? As we go along here, we increase the bending moment, we get less vertical or axial force capacity.
Yeah, I meant there was more force, so yeah. I
Okay.
know what you're talking about.
So this side here, it makes sense. So this side here, it makes sense as we increase bending moment. So this direction here, look at the x. So this is x. Think about as mathematics, huh? So this direction is x. So this direction here, we're increasing the x, which means we're increasing the moment, and simply the axial force will decrease. Really, what doesn't make sense, and it will have hard time for you to understand, this portion here. This portion here, which is from this point going down. Please watch this. It's very interesting, huh? Watch this. So this point here, I am supporting how much moment? We're supporting this much moment. This much moment, okay? I'm gonna move it here so you guys can see. So we're supporting this much moment. How much the axial force? 0, no axial force. And if I start to add axial force, it means I'm going this way, the y is increasing. Guess what? See what happens? When I add axial force, guess what? We're increasing the moment capacity. And this will drive you crazy, right? So you can see this is my moment. So this is my moment of resistance, okay? So if I add axial force, this much from here to there, okay? So this will increase. Looks like this MR is more than this MR. Would you agree?
Yes.
Yeah.
So what is the secret? It's about the failure mode. The failure mode. So if you remember our failure mode here, if you guys remember when we studied this and talk about tension, compression, and balance of failure, we have almost exactly the same thing. Guys, in this part here, what really controls the failure is the failure of the steel. If you guys remember that we design our beam to be tension failure, correct?
Yes.
Okay, so if I apply an axial force while the failure is controlled by the tension in steel, and I'm applying, remember, I'm applying compression force. So the section is it will fail as controlled, so it will yield first. Okay, I know that this long shot, and it has been few months right now, but I'm gonna remind you, if I'm designing a beam, forget about the column for now, please. So I'm designing a beam, and in beam design, I told you that we need to make it a tension failure where the rebar yields first. And remember, the rebar was in tension, so it will yield under tension. However, I'm applying a compression force. Am I helping rebar or worsening it? What do you think? The rebar was yielding in tension, and I apply for the entire section a compression. Am I helping the rebar?
Yes, you are helping the rebar.
I'll say it one more time. So it looks like only Jerry is following.
No, you're making it worse.
Okay, so I mean, let me draw the section. Okay, so let me draw the section. So here is the section. Probably that's the only way you can understand. So this is the strain diagram, compression on concrete, and then it goes this way. And on this bottom side here, I have my rebar. Okay, probably I will give it color. Line type. So this one here is my rebar because I'm applying bending moment. And we know that this guy will fail first in tension before this guy fails in compression. Okay, I'm asking you now, I will apply compression. Okay, so I'm gonna say here compression. Okay, and then remember this guy was tension. So I'm asking you, when I apply compression to my section, remember concrete was good, was okay, but rebar failed first in tension. So if I apply compression force together with the bending moment, am I helping my rebar or adding more stress to my rebar? Remember, this is tension, and I'm applying compression to my section.
You're adding more stress to your rebar.
Actually, I'm applying less. So what happened here, when I apply compression, this guy here will increase and this guy will decrease. Guys, look at the sign. The rebar is in tension, so probably I can write it here. So this, I'm gonna clean it a little bit, so please give me some time. So I said concrete is in compression, so C, and rebar and this in tension. And remember, this is without adding any compression force. This under bending. Okay. If I apply compression together, which means I'm going to add this. So this is my stress diagram due to the axial force, and this will be C. So this will be a C compression. Okay. So I can tell you we're kind of adding, so this plus this. So that what you see on the left is the stress from the bending moment, and what you see on the right is the stress from the axial force. Okay, and then finally, what will be the resultant? You simply have to add both of them. And remember, we're adding here compression plus compression, so the compression will increase. And here on this side, here we're adding tension to compression. I'm asking you, the tension will increase or will decrease?
Or will decrease.
Are you guys still struggling? That's called superposition. We're adding two diagrams. A diagram, a stress diagram due to moment only, and a stress diagram due to axial force only. Hello.
Yeah, what I'm following you.
So because you said you were making worse, so
Well, I'm slow. It takes me a while to catch up. I'll catch up. Don't worry.
okay, so can I get somebody else, please, to confirm? Are you following? What I'm trying to say here is that when we apply an axial compression on a beam section, it helps our rebar because it reduces the tension in our rebar. Are you following? Please say something.
We are following, Doctor.
Okay, thank you so much. So that's how I can explain for you. If we start to adding some axial force compression, you can say here, or you can tell that we get a little bit more increase in the moment capacity, and that's the reason here. Because simply this one here is a pure, so this diagram here for pure bending moment, so no axial force. And I said here, in this case, rebar will yield first, okay? However, if I start adding a little bit of axial force, you can tell that when we add this diagram, which is simply compression, add to this triangular diagram, what it does, simply it gets more compression and less tension. Let's make it a number. For example, let's say that this was 15 MPa. Okay, and let's say this guy was 400 MPa. That's the yield, and we add here compression that gives a stress of, let's say, 5 MPa. 5 MPa. So what happens? What's your final? Look at the final. So the final, I'm gonna probably draw it here. So this is your final. The final is this side here will have 20, because 5 plus 15, that is 20. And this side here will have a 395. Okay, so this one here will be 395, and this side here will be 20 plus 5, 15 plus 5. This will be 20. Hopefully, this will make you visualize what happens if I add axial force together on a beam section. Okay? Hello?
Yes, sir.
Okay, so what happens? What if I keep adding? Look, so you can see this is little force. So what happens if I add a little bit more, a little bit more, a little bit more? At some point, what happens is at some point, this guy, for example, let's say this is 10. Let's say this has become 10. So if this is 10, what happens? This one will be 390, and this one will be 25. And if this guy's 25 MPa and my concrete is 25 MPa, forget about the phi c, just make it simple. It's for numbers. So in this case, what happens? It means concrete will fail first. Would you agree?
Yes.
Okay, so that will really what simply make the curve changes its direction. And so this point here, it is the balanced condition where concrete and rebar will fail at the same point. So from this point on, going this way on the curve, this one is called the tension failure. So on the curve, all these points here on the curve, so your assembly, your section will fail as a beam controlled by the steel failure. How about from this point on going to this direction? Simply your is mainly under compression, and the failure will be controlled by the concrete, which is a brittle failure. And there is nothing we can do. There is nothing we can do. Okay?
Tahir,
Hopefully. Mhm.
so I'm not understanding on. You're saying if we add axial compression, it increases the moment resistance, and your first example of 15 and 400 with the 10, well, that changed the moment resistance to 390. That's less. How is that helping?
The axial
390 is
force.
less than 400.
The axial force. So, Gord, I'm gonna remove this guy here and probably hide this one for now. Okay. So forget about this uniform diagram. This diagram we study so much and we say rebar yielded first, and forget. I mean, to make it simple, forget about the phi s and pi c. Okay. Let's talk about F field and F prime C.
Right.
Forget about resistance factor. Okay, so let's think about 25 MPa and 400 rebar.
Right.
So if you apply your pure bending moment and its tension failure, then your rebar will yield first. It means the stress here will become 400 and before your concrete crashes in compression. Would you agree? So the
Right.
stress
Yeah.
in concrete is less than 25, while the rebar already it's yielding, which means the stress is equal to 400. And
Oh,
remember
I
the 400 is tension and the 15 is compression. And what we're doing here, we're adding a force, and the force is not tension force. The force is a compressive force. And let's say this force will add for the entire section a 10 MPa. Look at what happens. This is compression, and so this is compression. So compression plus compression, it will increase the compression. However, tension plus compression, it will simply reduce the tension to 390.
Yeah, I see now. I just maybe it's too early for me, but it just when you say it's better, I think the number 400 should increase, but that's its max point. So it increases by reducing the amount of load. I see.
No, my friend, this is tension. I keep saying this is tension, and this is compression. That's the thing, like plus and minus. So because so it's a stress but reverse direction. So the
Yeah,
400 is
that's
tension, while the
that's
10
the
is
part that I was
compression.
getting confused on.
Okay, so that's why it's 390. It's not 410. It's not 410. It is 310, 400 tension, and we applied a force that causes stress over the section of plus 10 compression. So what you end up with, you end up on this side or 390 tension as well.
Yeah, I'm with you now. I'm following.
Okay. So anyway, so I would like to, since it doesn't help you guys, I know that you're not into math. So I'm gonna make those slides are for information only. And what they are about to kind of prove for you, same as we did with the beam. So please consider this slide and this slide here and this slide as well as for information. I'm not asking you to follow any derivation, but whoever is interested in the details, what they do is they are trying to see the behavior of the beam under bending moment and under axial force as well, same as I've done probably 6 weeks ago when I analyzed the beam, how it behaves when I replace the parabolic shape by equivalent rectangular block and blah, blah, blah. And I wrote sigma fx equal to 0, and I came with T equal capital C. Can anybody, or does anybody still remember this business? Like capital T is equal to capital C, all of that?
Yes.
This is very similar without any details, and please consider those 3 slides are just for information. You're not required to memorize them or even read them if you wish. But if you are interested to know how can we develop this whole diagram, like how can we draw a diagram which simply variation of bending moment and axial force, then here is the derivation, which is outside the scope of this course. Okay? Now, I think we need to break. It's 8:56, and we'll give you a 10 minutes break. I'll see you guys after 10 minutes.